All right, I think I might have skipped one here, folks. So we're just going to have a look at that. A device was used as a light meter. It had a 9-volt battery. V equals 9 volts. Calculate the current. I don't know how many amps when the resistance of the LDR light dependent resistor was 600 ohms. I'm going to pop that in. V equals I times R. I'm going to do my equation. We'll rearrange for I. I need to make I the subject, so I'll divide across by R. V divided by R will equal a certain number. 9 divided by 600. Put that into my calculator. Oh, not 610. Rather, 0.015. The current is 0.015 amps. All right, sorry I skipped that question, folks. Completely accidental. We're going to go for the last 7 pages. Some microwaves have a frequency of 1.5 times 10 to the power of 10 hertz. So frequency is equal to 1.5 times 10 to the power of 10 hertz. They travel at a velocity, a speed of 3.0 times 10 to the 8 meters per second. Calculate their wavelength. Sheep daddy equals I don't know how many meters. Velocity is equal to frequency multiplied by wavelength. I need to find wavelengths. To make wavelength the subject, I divide across by f. V divided by f is equal to sheep daddy. The velocity, now because of these strange numbers here, actually, I'm not going to do it like that. I'm going to do it V over F is equal to sheep daddy. And I'm going to write down that it is 3.0 times 10 to the 8 divided by the frequency 1.5 times 10 to the 10. I'm going to put that into my calculator. I'm going to press AB, 3.0 times 10 to the power of 8, down, 1.5 times 10 to the power of 10, giving me an answer of 0.02. So that will equal my wavelength. My wavelength is 0.02 meters. Looking at another energy transfer, and again, we've got it in kilojoules. Calculate the amount of energy wasted in 1 second in the generator. Well, total energy will equal useful energy added to the waste energy, meaning that 1,400 kilojoules will equal 1,300 kilojoules plus whatever energy is wasted. So if I do 1,400 kilojoules, take away 1,300 kilojoules, I will get the answer of 100 kilojoules, meaning that the waste is equal to 100 kilojoules. Calculate the efficiency of the generator. Now I'm going to do my efficiency, which I don't know. Can be either in percentages or in decimal points. It doesn't tell me, so I can do either that I want. Useful is equal to 1,300,000 joules. Total is equal to 1,400,000 joules. Efficiency is useful divided by total, meaning my efficiency is equal to 1,300,000 joules divided. It's wrong. 1,300,000 joules over 1,400,000 joules. Pop that into here. 0.928. 0.9285714, but we're just going to bring it down to 0.93. 9. There. Andrew skis down a hill. Go, Andrew. Andrew returns to the top of the hill and starts again. His mass is 67 kilograms. Now, again, this is higher tier, so please just be aware of that. Momentum is equal to mass times velocity. Higher tier only, but I'll do it anyway, just because it's fun. Momentum is about 2,000 kilogram meters per second, and his velocity is 31 meters per second. I've got to show this momentum to be about 2,000 kilograms per meter second, so I don't have to use that, but my equation is momentum equals mass times volume. Momentum equals 60, volume, velocity, not volume. 67 multiplied by 31 is equal to 2,077 kilogram meters per second. But just, yeah, that's what I've done. I'll just skip past the page one second. Whoa. He falls over. Oh no! And when his momentum is 2,000 kilograms per meter per second. After he falls over, he slows down by sliding across the snow. It takes 2.3 seconds for his momentum to reduce to zero. Calculate the average on force on Andrew as he slows down. Again, this is higher tier only, and it requires us knowing that momentum is equal to mass times velocity, that force is equal to mass times acceleration, and that acceleration is equal to v minus u divided by t. What we're going to do is we're going to substitute this a for that. Pardon me. I'm going to substitute this v minus u for that a. So I'll say that m times v minus u divided by t is equal to f, and that's the same thing as saying mv minus mu divided by t is equal to the force exerted. So end momentum, take away start momentum, divided by the time taken. So let's have a look. mv is his end momentum. That's going to equal 0 kilogram meters per second. mu was start velocity, so that's 2,000 kilogram meters per second. Time taken is 2.3 seconds. What is the force in newtons? Write down my equation. F equals mv minus mu divided by t. F is equal to 2,000 take away 0 divided by 2.3. So that'll be 2,000 divided by 2.32, 123 divided by 2.3, giving me an answer of 869, not 89, 869.565 newtons, 869.57 newtons should do the job. Forgot my units. The first motor has a power rating of 20 watts. Power is equal to 20 watts. The motor is used for 15 seconds. Time is equal to 15 seconds. Calculate the energy supplied to the motor. I don't know how many joules, but the equation is P is equal to E divided by T. I'm going to make E the subject of the equation, so multiply across by T. P times T equals E. And I'll write down that 20 times 15 is equal to E. I ran out of space because it's close together. 20 times 15 is equal to 300 joules. And my units are all okay, no prefixes, no nothing, but I will get a point if I'm able to rearrange correctly. In the second motor, the useful power output, useful, is equal to 18 watts, and the power input, total, was 24 watts. Calculate the efficiency of this motor. Try to find the efficiency. Remember, it can be a number in either percentages or in decimal points. Looking over, I don't see any particular unit that they want, so I can use either. Efficiency is equal to useful divided by total. Efficiency is equal to 18 divided by 24. 18 divided by 24 is 0.75. So the efficiency is 0.75, or if I times it by 100, I can get 75%. They mean the same thing. A technician is testing a filament lamp from a car. He connects the lamp to a test circuit with a 1.5 volt DC power supply. As we can see there, the circuit shows a lamp and the power supply. The current is 0.18 amps. So if I had an ammeter here, it would say 0.18 amps. Calculate the resistance of the filament lamp. The voltage is 1.5 volts. I'm collecting my terms. I don't know which equation I'm going to use yet. And it's trying to ask me to calculate the resistance in ohms. The equation that I know is V equals I times R. I must make R the subject of the equation. Rearrange to find R, so divide across by I. R is equal to V divided by I. R is equal to 1.5 divided by 0.18. Put that into my calculator. And it will be 8.3333333. I'll just move this down because it might be a place for me to write it. Yes, 8.3333333 ohms. Oh, I can't do that because that's 2 decimal points. That's incorrect. But I can just leave it as 8.3. A water tank drips water. Well, that's not a very good tank, is it? The mass of one water drop is this. M is equal to 0.00008 kilograms. Calculate its weight. I don't know how many newtons. Gravitational field strength is equal to 10 newtons per kilogram. I will write down that weight is equal to mass multiplied by gravitational field strength. I will substitute that mass is equal to 0.00008 times 10, giving me my weight equal to 0.0008 newtons. The water drop falls to the ground 13 meters below in 1.7 seconds. Calculate the average speed of the drop while it's falling. So the distance that my drop traveled was 13 meters. The time that it took was 1.7 seconds. The average speed, I do not know, but I know that the unit is meters per second. Speed is equal to distance divided by time. Speed will equal 13 divided by 1.7. Put it into my calculator. Not 1.8. And it is 7.647. 7.65 meters per second will do it for us. You could, even if you wanted to, do 7.7 because it only gave us one decimal place in the question. Some students investigate a model of the craters produced by meteorite impacts. The ball drops into a tray filled with sand. They use 6 balls with different masses. Clever. They drop each ball from the same height. Very clever. So we've got to control. This photograph shows the sand after several balls have hit. When one ball hits the sand, it has a velocity of 6.2 meters per second. V is equal to 6.2 meters per second. It has a momentum of 0.46 kilogram meters per second. Remember, this is only for higher, or higher, as I've written there. Calculate the mass of the ball. Mass is equal to, I don't know, kilograms. But it's still good to tune in and figure out and remember how to rearrange equations. Momentum is equal to mass times velocity. I shall divide across by v to make m the subject, making p divided by v equal to m. Putting my numbers in, 0.46 divided by 6.2 will equal the mass of the ball. Very small ball, 0.46 divided by 6.2 is equal to 0.742. 0.742 kilograms. 2 decimal places there. I'll give it as 0.74 kilograms. And there's another page up here. Yes, there is another page. Oh, that's so exciting. And I'm very happy to be doing this. The ball takes 0.17 seconds to come to the rest. Its time is equal to 0.17 seconds to come to rest after the ball hits the sand. Calculate the average impact. Why did you do that? Why are you doing this to me? T equals 0.17 seconds. I think it understood that I was being sarcastic when I said I wanted to do that one. But you know what? Never mind. It's just a computer. Now, to find this then, to find the force, I need to use the equation. This is, again, higher tier only. Force is equal to mv minus mu divided by t. That's not even mu. That's just a squiggle. That's how a doctor would write the word paracetamol. Funny joke. The momentum was 0.46 kilogram meters per second, and the velocity was 6.2 seconds. But I don't need that. I just need the momentum, which was 0.46 kilogram meters per second. The initial momentum was 0.46 kilograms meters per second, and it's asking me to calculate F in newtons, and the final velocity will be 0. Final momentum will be 0 kilogram meters per second, because an object that isn't moving hasn't got momentum. Write out my equation. F is equal to mv minus paracetamol divided by t. And I'm going to put in mv being 0.46, take away 0, divided by 0.17 seconds. Pop that into my calculator. 0.46 divided by 0.17, giving me average impact force of 2.706 or 2.71. The cyclist in this picture is traveling at a constant velocity. You go, cyclist. Her muscles produce a driving force of 15 newtons, and we can see that. The cyclist accelerates at 1.4 meters per second squared. The mass of the cyclist and bicycle is 60 kilograms. Calculate the resultant force. Now, this is really interesting. So this is going to get us the force of the driving of the legs down there. So we'll figure out what the force is. I don't know what this force is in newtons. I know that the mass is equal to 60 kilograms and the acceleration is 1.4 meters per second squared. Remember, that does not mean that I square 1.4 meters. That is not how we do things. It is incorrect. Take it away. Take it away now. Take it away now. Stop freezing. Why are you frozen? Okay, it's gone. So I'm going to figure out my force. Force is equal to mass times acceleration. Force is equal to 60 times 1.4. Put that into my calculator. 60 times 1.4 is 84 newtons. So if the force of the cyclist is 84 newtons, Oh, I have no idea what this is. The cyclist in the picture is traveling at a constant velocity of 15 newtons. The total amount of force is 15 newtons. Oh, so this must be a different question. Because the resultant force, that is 15 newtons. The cyclist in this picture is traveling at a constant velocity. Your muscles produce a driving force of 15 newtons. The cyclist accelerates at 1.4 meters per second squared. The mass of the cyclist is this. Calculate the resultant force. Well, I've got no forces acting opposite it. The resultant force is 15 newtons. Unless it's 15 plus 84. Could be 99 newtons, that would be. Yeah, I'd say 99 newtons. But then where's the force coming from? 15 newtons. This must be a changing question. So resultant force is going to be 15. I'm making 84 newtons. Muscles produce a force of that. Right, you know what? I don't know. Question mark that when I'll ask Mr. Patrick. But I'll look at this one. The cyclist accelerates for 8 seconds. Time is equal to 8 seconds. Calculate the increase in velocity during this time. Okay, maybe it's this. The acceleration is 1.4 meters per second squared. I don't know what the initial velocity was, though, in meters per second. And I don't know what the final velocity was in meters per second. I could assume that the start velocity is 0, but again, I think I'm missing something here on this one. Or I could just be super duper tired. A is equal to v minus u divided by t. 1.4 is equal to the end velocity, which we do not know, minus 0 divided by 8 seconds. Multiply across by 8, and I shall get my answer. 8 times 1.4, giving me 11.2. The increase in velocity was okay. So there must have been some missing data there, or a velocity I don't have. But at least we've done some maths. Okay. The average speed of a P wave in the mantle is 12. Oh, we've done this one already. Oh, but it's okay. We'll do it again. Speed is equal to 12 kilometers per second. A P wave travels vertically down the surface and reflects off the core mantle boundary back to the surface. It travels a total. Oh, look, I think I might have missed this last time. Anyone who's still watching these videos, it travels a total distance of 5,800 kilometers. There is the Earth and there is the core. That's what happens when you do things too quickly. Earthquake travels down and comes back up. The total distance of those both legs, leg going down, leg going up, line A and line B, A plus B will equal 5,800 kilometers. Oh my God. So if it's an equal journey both ways, I don't know what those numbers are, but that's okay. If I divide 5,800 by 2, that will give me the amount of distance in one leg. So I'll do that, 2,900 meters. That is the distance that one of these things travels. Calculate the total time of travel for the wave. Oh, no. Okay, it doesn't matter. I don't need to do that. However, it may pop up. If it asked you how long it took down to get to the core, then that would be a different thing. But it's not. RTFQ. RTFQ. Even the best of us make mistakes. The total distance traveled was 5,800 kilometers. Now, because I've got kilometers per second and kilometers, I'm not going to turn this into 12,000 meters and 5,800,000 meters either for calculating the total time of travel of the wave. I'm just going to do speed equals distance divided by time. I'm going to rearrange this equation to find that time is equal to distance divided by speed. That time is equal to 5,800 divided by 12 and get that answer. 5,800 divided by 12. Oh, and by the way, don't you worry. You are going to have more than enough space in your actual GCSEs to do this. It's just because we shrunk them down. Well, not me. This is Mr. Patrick's glorious sheet. So, yeah, he gets the kudos, the credit, the well dones, the attaboys, the pat on the backs, the thumbs up, the smiles, the rounds of applause, the bows from the crowd, and the exeunt pursued by bear. A child is stationary on a swing. The child is given a push by his brother to start him swinging. His brother applies a steady force of 84 newtons over a distance of 0.25 meters. Calculate the work done by this force. F is equal to 84 newtons, and it is working over a distance of 0.25 meters. To find E, I don't know how many joules. E is equal to, I don't know how many joules, but I will use the equation E is equal to F times D. Work done is energy, same thing, 84 times 0.25. And again, we can do this in our heads, but we're going to pop it into the calculator anyway. 84 times 0.25 is equal to that count. All right, no, sorry, hang on. There we go. Press the wrong button. 21 joules. State how much energy is transferred by this force. It is the same thing. Energy transferred, work done are the same thing. After several more pushes, the child has got a kinetic energy of 71 joules. The mass of the child is 27 kilograms. Show that the velocity of the child at this point is about 2.3 meters per second. Now, this is nice because you can do something a little bit silly and mess up and get a strange answer and know that you've done something a bit silly, and you can go back and check it. EK is 1/2 mv squared. I'm going to rearrange this equation because it is a nice one to look at. EK over 1/2 times m. That is the same thing as a square root of 71 over 1/2 times 27. Popping that into my calculator, I'm going to do the square root sign. I'm going to press AB. I'm going to write 71 down. I'm going to do 0.5 multiplied by 27, and I can see in my calculator that it is exactly what I've written down there, so I know it's correct. My velocity is equal to 2.29 meters per second, and that is about 2.3 meters per second. Well, what? No, please say I didn't delete. Okay, there we go. Don't worry, I didn't panic. Nobody panicked. Where have you gone? Where are my questions? I've just done that. Okay, go down. Kettle. Oh, I love a cup of tea. Student uses an electric kettle. It works from the 230 volt mains supply. Remember, if you lick the mains, your tooth will hurty. Tooth hurty. This is a number you need to remember. The power of the kettle when it's heating. Power is equal to 1.8 kilowatts. And the sneaky hobbits are there again because we don't want kilowatts. We want watts. Times, no, we don't want, that wasn't me asking a question. I was just saying that we want watts, not asking you what we want. So the power is equal to 1,800 watts. The mains voltage is 230 volts. Calculate the current in the kettle. I do not currently know what that is. P is equal to I times V. Rearrange this equation. I'm going to divide across by V, so I can have P over V equals I. I will write 1,800 over 230 is equal to I, and I shall get my equation to be 1,800 divided by 230. My current will be 7.826, so we'll leave that at 7.832.888. All right, you know what? This is just an 8, and we're going to do that. Don't do this in the GCSE, folks. The kettle is switched on for 2 whole minutes. Goodness gracious, did they not know that the price of petrol is rising? And I don't want minutes. I'm going to multiply that by 60 so I can get that as 120 seconds. Calculate the total amount of energy transferred in that amount of time. Now, I've got voltage, I've got current. So what I could do, I've got actually 2 options here. I can do that energy is equal to voltage times current times time, or I can use P equals E divided by T, because this will get me my energy, and also if I multiply T times P, that will get me my energy as well. I'm going to go for the easier option, because power is 1,800 volts, suddenly from Germany or something. 1,800 will equal to E. 1,200 multiplied by 1,800. 216,000 joules. Just to show you that it's the same thing, I shall do 230 times the current, which we just worked out to be 7.8. We'll do 3 multiplied by the time that it was left on for, 120. Now it'll be sort of the same. You'll get the marks for both of those because it didn't tell you to use any particular equation. But when I pop that into my calculator, I get a slightly more accurate 216,108. But let's round that to 3 sig fig 1, 2, 3, and that rounds down to 216,100, and it's the same answer. So sometimes you can use the same equation for both. No, different equations to get the same answer. That's what I meant to say. Ooh, what's this? Ooh, what's this? Waste gas contains smoke particles. Okay, the diagram shows how smoke particles can be removed from waste gases as they rise through a chimney. That's cool. All right. Chimney wall, metal plates. Why have we got metal plates? Look at that. 400 volt power supply and a metal grid. And that metal grid appears to be in some kind of a circuit, but I don't really know. Waste gases and smoke particles. That's interesting. There is a current of 1.4 amps between the grids and the plates. So I is equal to 1.4 amps between the grids and the plate. Calculate the charge transferred by this current. It's asking me to find the quantity of charge in coulombs in 2 minutes. Sneaky hobbits. Multiply by 60 so that we can get sneaky. Do you know what that's from? Lord of the Rings. Sneaky fat hobbits. And I would do an impression, but this is being recorded, so I'm not going to do an impression. Q is equal to 1.4 times 120. 1.4 times 120. That gives me 168. Q is equal to 168 coulombs. I shall write it down here. Don't forget that. The potential difference between the grid and the plate is 400 volts. Calculate the electrical energy transferred in 2 minutes. Oh, it's the same. Is it EQV? Okay. So got a voltage of 400 volts. It's asking me to calculate the energy transferred in time of 2 minutes. And I'm not going to do that because I'm not an idiot. Multiply it by 60, we get 120 seconds. Now, there's two things that we can use here. We can either use E is equal to Q times V, or we can use E is equal to V times I times T. Let's substitute both at the same time. I feel crazy right now. I feel like I could do anything. I'm on top of the world. E is equal to 400 times the current, which is 1.4, which we had in the past question, multiplied by time, which is 120 seconds. Let's have a look at that. 600. Last time someone was on top of the world, it didn't end very well because I saw that in a movie about a boat. And let's hope our GCSEs are nothing like that. 400 times 1.4 times 120. This one gives me 67,200 joules as well. So both equations finding both the same thing. It's not surprising really if you think about it, because Q is just I times T. And if I have I times T here, that's the same as Q. But still, it's nice, simultaneous. Not simultaneous equations, actually, that's something different. Okay, the graph shows how the velocity of a small car changes with time. We should stop saying small, okay? It's less than large. Use the graph to estimate the velocity of the car at 3 seconds. Oh, we've done this one too. There's 3 seconds, go across. I estimate the amount of velocity to be 2. The devil take you and whatever microprocessor you have in your brain. Just stop it. Line goes up at 3 seconds, goes across to 10 meters per second, and it is estimated. Calculate the acceleration of the car while it is speeding up. It is speeding up when the line is going up, and this line is going up in an upwards direction. Can I just delete that? Yeah, okay. So it's asking me to find acceleration. I don't know, in meters per second, when it is speeding up. So for that, I will need the end velocity, the start velocity, and the time taken for the acceleration to change. End velocity was 20 meters per second. Start velocity was, rather helpfully, 0 meters per second. The time taken for that change was here, 5 seconds. A is equal to V minus U over T. A is equal to 20, take away 0, divided by 5. And you know what, kids? I think I can do that in my head. 20 divided by 5 is 4 meters per second squared. The diagram shows a car and passengers at the start of a roller coaster. Ugh, I hate roller coasters. At an amusement park. I'm just gonna change that because it's not fun. I'm just gonna say a horror park because earthquakes. Roller coasters are awful. An electric motor pulls the car from A to B at a steady speed before dropping off the edge, simulating death. But it doesn't say that in the question I was just showing you. The total mass of the car and the passengers is 9,500 kilograms. A prime fool who can't wait to get smashed against the ground. Calculate the amount of work done. It's asking me for work done in joules on the car and the passengers. And it's giving me a gravitational field strength of 10 newtons per kilogram. Well then, what work done, mass, gravity? There must be something more here. Well, look, we've got two choices. We've got 25 meters and we've got 18 meters. That's the distance that it moved and that's the height that it went up. Which one are we going to use? Well, because 25 meters isn't doing work against gravity. So yes, it's going up in an angle, but it's actually only going up 18 meters against gravity. So the work done is the work done against the force that's moving down. So you might be tempted to use 25 meters and then do this equation here, E is equal to F times D. But this distance isn't the distance that it traveled on the angle, but rather the distance it traveled up. So I'm going to use EP equals mgh. The change in gravitational field is equal to the mass times the gravity times the change in height. So I'm going to find the work done to be the mass of the car is 9,500 kilograms times 10 times the height of 8. Why do I always do that? 18 is not the same as 10. 9,500 multiplied by 10 multiplied by 18. Oh, I just added it. I wonder how many times I've done that. I hope somebody finds a mistake. I hope somebody watches these videos. The work done is 1,710,000 joules. The car is released at B and continues down the track, hopefully, but nobody knows that. State the maximum possible kinetic energy of the car and passengers at C. Well, up here, I have got 1.71 kilojoules. That's not true. I've got 1,710 kilojoules. Goodness gracious me. Now, when this car goes down, the amount of kinetic energy that will be transferred... I drew an arrow! Oh my God, look at that. That's so cool. The amount of kinetic energy that's transferred will be equal to the amount of work done that was used to get it up there. So the amount of kinetic energy will be the same as the work done. Hopefully, you've seen this a lot of times. When the car and passengers reach E, they have a total momentum of 1,500 kilograms meters per second. And E is this little bit right here. The total mass of the car and the passengers is 9,500 kilograms. Calculate the velocity of the car. Please remember this is higher, but by now you should be able to figure out what it is because you have seen me do this question quite a few times. Kilogram meters per second. That is the momentum. The mass of the car is equal to 9,500 kilograms. Calculate the velocity of the car in meters per second. Momentum is equal to mass times velocity. I'm going to rearrange this equation, divide across by m to find P is equal to P divided by m. I'm going to pop my numbers in. 150,000 divided by 9,500 will equal you 15. Oh, Jesus, 15. I'm going to put my numbers in here actually, just because I jumped the gun there a little bit. 15,000 divided by 9,500 is equal to the velocity 15.79 meters per second. You foolish, foolish people. Oh, no. Yes. Oh, we're done. Ladies and gentlemen, we're done. It's all finished. We've done all the questions. There is no more I can ask of you. You marvelous human beings. Oh, except those of you who are doing higher. They're the higher questions to do over there. But we're not going to talk about them right now because it is currently, 6 o'clock, and I'm pretty sure they're about to lock the school on me. Thank you very much for paying attention. Good day. Oh, for goodness sake, now.